for our project, we did predicting crab age with machine learning. And this is for the machine learning class, of course. And in our group, it's just me, Brian Lucero, and my teammate, Justin Hang. On the next slide, you'll see we're going to start off with the abstract, which is what we wrote in our paper. It's a really simple, really straightforward. Machine learning can be used to predict the age of crabs, and it can be more accurate than simply weighing a crab to estimate its age. There's several different models that you can use through support vector regression. That was actually the best model that we found to be most accurate in this experiment. So more in depth on like the problem and why it's important and the strategy that we came up with to like actually make a solution to determining the age. First, let's start with the problem. So it's quite difficult to actually determine the crab's age just because, of course, there's smaller crabs and there's bigger crabs, so you can kind of tell age that way. But when you get down to like the crab's actual molting cycle, one of the like features of a crab is it has a shell, right? And it's hard or it's soft. When it molts, it's soft. So even if it's an adult, it can be thought of as really young because it's soft and it just molted. So then like it's actually quite hard to determine the age. So the reason why this is an issue though is because the failure to harvest these crabs at like the optimal time causes a waste in business essentially, and like higher costs, and you're just not going to get like the business like I guess efficiency that you would normally get or that you could get. So that's why it's important. Even though there's beyond a certain age, there's negligible growth in the crab's physical characteristics, and thus like it's important to time the harvesting to reduce that cost and increase profit. So our solution is prepare crab data from a data set that we found on Kaggle and use it to train several different machine learning models. So we were like, basically we take the crab data, like given physical characteristics of it, and we're going to use those models to determine the age of the crabs. On to the next slide. That one probably could have been shorter. So I'll give a little bit more background on that. So we're actually going to assume in this prediction system that a crab is mature and ready to harvest after 12 months. They grow pretty fast and they're pretty much fully grown, ready to go, ready to harvest at 12 months. So we're going to actually ignore other features that affect the crab's harvestability, like such as egg-laying crabs. We're also going to predict age rather than weight, since machine learning is more applicable to actually predict. It's kind of like pointless to predict weight because, I mean, all the models that we would choose or like that we would implement, like it's gonna be quite like accurate to predict their weight, but age is what's like more important in this problem at least. So as far as like going back to the data set that I mentioned that we got from Kaggle, there's over 1,000 samples. It's closer to like about almost 4,000 individual records. So we have different features for each crab. There's sex, length, diameter, height, weight, shucked weight, scare weight, shell weight, and age, of course, which is our classifier. And originally, like as you can see, it's a all like we have discrete and categorical, or like we were thinking about like whether we should do a categorical classifier or like a discrete classifier or like a something that's like maybe even continuous too. But eventually, like we decided that as far as like feature selection goes, data pre-processing and everything like that, which we'll see in these later slides, which feature like selection we're going to actually go with. So next slide. So yeah, for the data pre-processing, we actually converted sex to numerical values. So that's to like make the data set actually have all the same data type. And we also did a test train split. So used to saying train test, but for that train test split, we did test size 30%, and train size 70%, of course. Moving on to the rest of it. So this leads to like feature selection. What we did is we used the Pearson correlation coefficients. So we're going to ignore gender altogether, or like, ignore sex and keep all the other features. So greater than 0.5 is pretty high correlation. So um, we use this to actually determine the features. As far as like the methodology goes, like if you want to get like a general kind of sense of like the prediction system like workflow, you start with like the problem domain, which I mentioned in the very beginning, which is the age prediction of crabs. We're gonna like filter it out, and or like we're gonna like slowly branch out to like determine like the various like I would say like introductory features, or like base features, or base like process steps, which is data representation. So we get the data set, we did some pre-processing to it, we get a function, or like we determine like the training and test set, and then basically what we're going to do is we're going to use a metric to actually determine like what kind of like function it is, or like to evaluate it essentially. And we used average error rate, so that's on both training and test data. So then eventually we decided on three algorithms: KNN, which is K nearest neighbors, MLR, which is multiple linear regression, and SVM, support vector machine. And so you get three different predictive models, and this combined makes the prediction system the aggregate model results. And finally, you get either useful predictions, which is like what you want to see, like a good prediction system, or instead you also get like domain insights as well. So maybe like other interests and like how you can tweak this system to um, I guess get different insights, get different uh, inferences and whatnot. Moving on to the methodologies of like the main three models that we have. So we have a three machine learning models and one baseline model. So the one baseline model just being the linear regression with weight. So that's just simple linear regression, just a line, and it's weight versus age. So I guess that's kind of like the introductory, like almost test model. It's very, very simple. Then when you moving on to k nearest neighbors, multiple linear regression, support vector regression, just like I mentioned earlier. And we use the scikit-learn Python libraries to implement those. Moving on to next one. So the first one we have is multiple linear regression. So for this, the methodology that we went with, or that I decided on, is just straightforward, simple vanilla feature selection, which is we remove the gender. So we took the data set, did some feature selection. We did the Pearson coefficient correlation test, basically. And then we did the train test split, trained the model, evaluated the results, and we got the measure the average error. Then moving on, I'll hand it over to my teammate Justin. He's going to go over the methodology and the rest of the presentation.
All right, thank you, Brian. So for the methodology for the KNN, we needed to find what value to use for K. And in order to do that, we had to plot the average error from 0 to 30 for K and basically figure out which value was the best in that one. So you can see on the graph on the right that K seems to plateau around 15, 10 or 15, and around like 20 is where it starts to get kind of even. So we decided on K equals 20 for our K value. All right, and moving on to the results. You can see this is kind of a messy graph of every single model laid on top of each other. We'll go over each model in detail. And moving on to our baseline. So again, this was linear regression, where we only used weight to determine the age. And the average error was about basically 2 months. You can see on the graph on the right that a lot of the times the peaks were the problem areas and it wasn't able to correctly predict those. Just overall, the model didn't predict it very well. And then moving on to our KNN model, already you can see it outperformed the baseline. And it was actually slightly the worst out of 3 machine learning models with an average error of 1.6 months. And it was not very accurate at predicting the ages that were under 12 months, but it was okay at predicting like some of the peaks. You can see the data set around like 33, it was able to correctly predict that one. Overall, it was a decent model. So for multiple linear regression, this one also outperformed the baseline. It's very similar to linear regression where it uses the features and it tries to fit a line through it. But of course, since this one has more features, I shouldn't say always, but it usually does better. So, and it was also better at predicting mature ages above 12 months. Overall, a good model, and its average error was about 1.5 months. Again, you can see the graph on the right. So for the results for the support vector regression, this one also outperformed the baseline. And it was pretty accurate at predicting ages under 12 months compared to the last one, which was better above 12 months. This one actually had the least amount of error, where the average error was 1.4 months. Again, you can see on the right, for most of the, the troughs, it actually fit those very well to the model. It had trouble predicting some of the peaks, but overall, all of the models had trouble predicting the peaks. So yeah, those are our models, and this is just a table summarizing the results. The simple linear regression, which was the baseline, had an error of 1.9. So overall, our models beat that by about 0.3 months in errors. And the support vector regression did the best at 1.4, but it was very close to the other two. So in conclusion, we learned that machine learning did outperform the simple linear regression. And on average, the models had an error of about 1.5 months compared to the baseline, which had 2.0 months. Support vector regression did have the slight lead, but multiple linear regression and k-nearest neighbor were also good predictors. So overall, we could say that any of the models could be used to predict grab age pretty well. The predictions were good up until 12 months. And we think that the reason this is because after 12 months, when the crabs reach maturity, the features no longer, for example, the weight, the height, they no longer increase. So that's probably why our models had trouble predicting crab ages past 12 months. So in the future, if we want to improve our model, anytime the features were above 12 months, we would probably just hard set them to 12 months. And it would probably have less error overall. And that's the end of our presentation. Thank you, and we'll take questions now. All right.